Okay, last question. Finally. It only took an hour and a half. Okay, question 4. I think this question was probably the trickiest of the 4. The first part is fairly straightforward. It's asking us to show that dy over dx equals something. So it tells us what our answer should be. We just need to be able to get to that answer. So, well, what is dy over dx? That's our derivative of y with respect to x. So let's just take our original curve and differentiate it with respect to x. D over dx of x squared plus 4y squared equals 7 plus 3xy. All right, derivative of x squared with respect to x, that's just 2x. Derivative of 4y squared, that's going to be 8y times dy over dx. The derivative of 7 is 0. The derivative of 3xy, let me actually refresh it really quick so you can see what I have so far. We're going to have to use the product rule here. We're going to end up with 3y plus 3x dy over dx. You could have also written it the other way. It doesn't make a difference. You could take a lot of different routes from here. We're just solving for dy dx at this point. I'm just going to try to get my dy over dx on the left side and then get everything else on the right. So I'll treat this similar to like an algebra 1 problem. It is an algebra 1 problem. This is a linear equation. Minus 3x dy over dx minus 2x minus 2x. You actually write it in a different way. Actually, I'm not going to solve it out like an actual linear thing. I'm just going to rewrite it 8y dy over dx minus 3x dy over dx equals 3y minus 2x. And boom, you can tell, or I can tell that I'm on the right track because I got this 3y minus 2x, and I see a 3y over 2x on my numerator. If we look at our left-hand side, we can factor out a dy over dx. So we get 8y minus 3x times dy over dx equals 3y minus 2x. And finally, we're just dividing by 8y minus 3x. We get dy over dx equals 3y minus 2x over 8y minus 3x. And boom, we showed that dy over dx equals this thing right here. Awesome. And we're going to use this piece. Part of the reason that I gave you this answer is because even if you weren't able to do this, you need this piece in order to do the other pieces. Okay. Part B, it says show that there's a point P with x coordinate 3 at which the line tangent to the curve at P is horizontal. All right, let's start with this piece right here. It says line tangent to the curve at P is horizontal. This question is worded really trickily, but it's actually not that bad. There were 2 points on this question. The first one is, it's actually kind of backwards. The first thing that I expected you to do is find the y coordinate and then do this part up here. because it tells us that the line tangent to the curve at P is horizontal, so we want 3y minus 2x over 8y minus 3x. This is the slope of our tangent line. And we want the slope of our tangent line, we want our tangent line to be horizontal. Well, what does that mean? It means that the slope of our tangent line is 0. So we want our derivative to equal 0. And we want it to equal 0 when x equals 3, specifically. When x equals 3. So let's just substitute in a 3 for x, so we get 3y minus 6 over 8y minus 9 equals 0. And then we're just solving for y. Solving for y, we get 3y minus 6 equals 0. Just multiply both sides by 8y minus 9. We get y equals 2. And that's one point right there. We found a y-coordinate where the line tangent is horizontal at the point 3, 2. And now we need to show that this point is on the curve, which we haven't really done that before in class. Although I expect you would have done it in part of your pre-cal classes, probably. All we're going to do is we're going to take our point 3, 2, and we are going to substitute it in to our original function and see if this is a true statement. Because if this point 3, 2 satisfies this equation, then we're on that curve. Okay, so we have 3 squared is 9 plus 2 squared is 4 times 4 is 16 equals 7 plus 3 times 3, 9 times 2, 18. That gives us 25 equals 25. And boom. Those are your 2 points right there. Getting to y equals 2, and then showing that this point is on our curve. Okay, and now find the value of dy, of d squared y over dx squared. Does it have a minimum, maximum, minimum, or neither at point P? Justify your answer. Okay, so first part, we need to find the derivative at point P. So let's just start with d squared y over dx squared equals, this is the derivative with respect to x at this point here. So let's take, the derivative with respect to x of our derivative. So let's take our derivative. What rule do we need here? We need the quotient rule. So our low d high, 8y minus 3x times our derivative of our high, which is 3 dy over dx minus 2. So our low d high minus high d low, 8 dy over dx minus 3, all divided by 8y minus 3x squared. Okay. And now we're just plugging in our values, and this is I'm going to make a clever observation here. Well, in part B, we saw that the line tangent to the curve at P is horizontal. What did that mean? It means dy over dx, our derivative, equals 0 at this point. So all these dy's over dx's, those are just going to become zeros. And everything else will just become part of one of our points, 3, 2. So we have 8 times 2 minus 3 times 3 that just becomes negative 2 minus 3 times 2 minus 2 times 3. 8 times 0 is 0, minus 3, divided by 8 times 2 minus 3 times 3 squared. Okay, and looking here, 3 times 2 minus 2 times 3, that's just 6 minus 6, that's 0, so this whole term will just go to 0, so I'm not even going to worry about it. And we're going to end up with, I'm going to do quick mental math, and I'll point out the other observation that I'm making. That now that this whole term has gone to 0, if you follow this, great. If you don't, you can work the mental math out on your own. This thing is divided by itself, and this one is squared. So this is just negative 2 divided by 8 times 2 minus 3 times 3. Like these are common factors on our numerator and denominator. So this one goes away, and this one just gets an exponent of 1 using our exponent rules. So we get negative 2 over 16 minus 9 equals negative 2 over 7. Okay. And this is our derivative at that point, negative 2 over 7. This is 1 point right here. Now, is it a local maximum, minimum, or neither? Well, now we're going to think about our derivative tests. Our second derivative is negative. So what does that mean about our function? It means, well, our function is concave down. I'm just going to draw a little picture to help me get an understanding of what's happening. We're concave down. And what is our first derivative at this point? Our first derivative is 0. We have a critical point. So if we're concave down and we're at a critical point, in other words, our line tangent to the curve is horizontal, our point is going to be right here. And what is this? This is local maximum, minimum, or neither. Well, this is a maximum. So we're going to write local max at point P because dy over dx equals 0 and d squared y over dx squared is less than 0 at P. And there's our justification. And if you guessed that it was a local max, congratulations, you got yourself a free point. You could have guessed that, and I would have given it to you. And the second point was because of this part right here. dy over dx equals 0. We have a critical point. And d squared y over dx, where it is less than 0, we're concave down at point P. Okay. This is a fun question. I actually made this question myself. I didn't steal this one from College Board. This is a question similar to what you'll see a lot in your Cal 1 class if you take it again in college, where you're thinking about shapes as functions. So consider the semicircle defined by f of x equals the square root of 4 minus x squared. If you want to graph that, you can and verify that actually is a semicircle. And if you want to be even more specific, it's a semicircle with a radius of 2. And I could prove that, but I'll leave that for y'all to figure out. Is there a c such that f of c equals square root of 2? Well, that's important. Which of our theorems guarantees that f of c equals some value? So we're triggering some alarm bells here. Which conclusion will help us get to this answer? That would be our intermediate value theorem, because intermediate value theorem talks about our function value. So we need to do something with IVT here. So let's start writing out our stuff. So note, what is our hypothesis for IVT? Well, we need f to be continuous. F is continuous on 0, 2. And this is another instance where, if you watch the other video, I talked about not needing to write the interval. Here I am writing the interval because is this function continuous everywhere? Well, the answer to that is no, and because if I were to try to, let's look at 3. Well, 4 minus 3 squared is 9, 4 minus 9 is -5. F of x is not defined on that. So our function is not continuous everywhere. If you don't recognize that really quickly, knowing domains of functions, just write the interval every time. If you do notice it, you can save yourself a little bit of handwriting. But here we're not continuous everywhere, we're continuous specifically on that interval. We're continuous from 0 to 2. Okay, and then we want to find f of 0. Well, f of 0 is the square root of 4, which is just 2. And f of 2 equals 0. Because 2 squared is 4, 4 minus 4 is 0, square root of 0 is 0. Since there's several ways you could write this, as I'm going to do it. F of 2 is less than the square root of 2 is less than f of 0, which this is the math way to say. On our paper we wrote, we take on every value in between. This is the more mathy way to say that our value is in between f of 2 and f of 0. And I did f of 2 first because this is 0 and this is 2. Since f of 2 is less than square root of 2 is less than f of 0, by IVT, there exists a C such that f of C equals square root of 2 on 0, 2. Technically that should be open brackets at the end, but it doesn't make a difference. It's fine. Okay, and where are our points here? Well, one point is specifically for saying that f is continuous and we're using IVT. That's one point right there, and I'll highlight that in blue. We're noting that f is continuous on our interval by IVT. So that would get you 1 point right there. Just knowing which theorem you need to use. The second part is this observation that the square root of 2 is in between f of 2 and f of 0. And if you wrote it as since the square root of 2 is between 2 and 0, that's fine. There's other ways you could have written this. As long as you had something along this line that I'll say it this way, that the square root of 2 is between 0 and 2. As long as you had something along those lines, that was your second point. And then the third point is our conclusion. So, what color do I want to do highlighting? I don't know what this is going to look like. It might look ugly, but we'll try it and see what it turns into. This was your third point right here. Oh, that isn't terrible. It's not my favorite color, but This is your third point right here, the conclusion to the intermediate value theorem. So when you're doing these theorem questions, a lot of them are citing the theorem, the correct theorem or a correct theorem that you can use, and then the conclusion to that theorem, that gives you most of the points, and the other part is just the stuff in between. So like if we did mean value theorem, I don't remember if I did mean value theorem on any of these other questions. Oh yeah, here, if I came back up here, I actually didn't even count it, but it's possible that I could have counted on this question here. You could have gotten a third point if I counted this one as 3 points for this work right here, that the average rate of change on 0 to 3 pi over 2 is 4 over 3 pi. But okay, that covers, I didn't put this question on your final because it was only worth 4 points and I wanted all 9-point questions, but that covers all 4 of the questions on the final. I hope this was helpful. I tried to take my time and really go through all my thought processes. If you made it this far through all 4 of these videos, I appreciate it. Thank you.